All right. Morning or afternoon, U12s. Today we're looking at 2D, which is a when for any vector we should be able to do what we call a projection and get the scalar um, respective values that we call resolutes. So the main application will be a vector in a Cartesian plane. We are able to express it in the direction of the x and y axis, and respectively the vector I and j of those axes. Those vector I and j are unit vectors, um, and that vector is also a projection of in, uh, in the direction of I and j. So we can do that in for any um, random or chosen vectors. We'll bring this back to a right angle triangle using Pythagoras, but uh, what you'll be just using is the what we've done previously is the scalar product. So on the graph here, any vector A can be expressed as a sum of two vectors u and w. In that right angle triangle, you can see that u and w are perpendicular vectors. That would imply that their dot product u w will be equal to 0. So here's a little bit of proofing. Have a look through it, how they achieve that. So they will start with breaking A as a sum. They will express u in terms of KB, as we want to do a projection of vector A in the direction of B. And we have W, that will be the difference of the two. As W will have to be perpendicular to B, we write the dot product, we do a substitution and expanding, and then we can determine the coefficient K, and then we have an expression, a nice expression of vector U, which is the component which is parallel to B. So it's a vector, and that quotient of scalar product is going to be a scalar amount. So the vector itself is called a vector projection, and that component is the scalar resolute. Another term instead of projection is resolute. So here is a vector, so for u in terms of b, and that will be the scalar resolute. Summary of that. So that's the how to express vector u. We can break it down as well in a different manner. When we do this, what it allows us to do is to separate into a new vector, and that vector is a unit vector. So we take that vector and we divide by its magnitude. That new vector that we call b hat is a unit vector in the direction of b. Again, this is a scalar amount, and that's what we call the scalar resolute. So that is another expression which is useful when you know the coordinates, but be mindful it can be written that if you have your unit vectors first. So there's two ways you can do that. It's really depending on the question, or with experience you will choose either this expression or the other one. Once you have u, to determine the perpendicular component, you write the difference of vector a minus u. That gives you this expression, and we can summarize vector a is equal to u plus w, and we substitute u and w by their representations as a vector resolute, and we get that sum. What you can also, it's about the language or the definition. Vector A can be also resolved as rectangular components. As U and W are perpendicular, they will form a rectangle. Let's look at two examples. So the first one, example 24. You may attempt example 23 first. It's a direct application. It's in your textbook. You can do that before attempting this one. To attempt this one, just pause the video and then we'll get back to this. All right, so let's continue with this. You have vector A and B, express the component. Don't forget that there's a J component that is equals 0 for here. No, note that it's vector A in the direction of B. The fact that it's directing towards B matters, so the direction towards a specific vector will dictate the expression you will be using. So first you do the dot product, then the magnitude of the vector in that direction. To find that scalar resolute, we do that dot product over the magnitude, and we simplify the third or rationalize it. Okay. Example 25. This time it's a little bit more work. You need to resolve that vector into rectangular component, one of which is parallel to that vector. So I'll give you pause the video, have an attempt at this. All right, back to this. First, you need to be just set the condition by annotating the vectors. That first vector, we're going to call it vector A. That second vector is vector B. Now, it needs to be parallel to vector B, so we need to do that in the direction of vector B. So looking at the expression here that we have for U from the original definition, the vector resolute of A in the direction of B is going to be that expression. So it's going to be a vector, and you're going to have to do a dot products and do that ratio. Go on with the calculation. So you do the products, you write the quotient times the vector b. So that's vector b and that quotient, and that will give you the vector resolute u. To find the w, the perpendicular vector resolute, just do a minus u. A minus u is here. You will have to expand the brackets and regroup the like terms or the respective vectors in the direction of I, j, and k, and then we can factorize that in that form. And what we do is we can write our vector A as the rectangular components. So you have u here and w over there. Notice as well, it's a good way to quickly verify that you haven't made a simple mistake in your calculation. Just do the dot product of u and w, and it will have to be equal 0, which is a good sign here. Right, so that's it for today, and I'll see you next time.